In the next 10 minutes, you're going to learn how to build a complete large language model from scratch using nothing but Python and one AI tool. We'll go from 0 lines of code to having your own ChatGPT running on your computer. Now, most people think you need a PhD in machine learning or years of coding experience to build something like this. But here's what's crazy. With the right AI tools, a complete beginner can create their own language model in just a few hours. But we're not just gonna show you the pretty end result, we're going to tackle the 3 biggest challenges that stop most people. Setting up the development environment without wrecking your computer, processing massive datasets without your system crashing, and building a transformer architecture that actually works. And here's what makes this different from every other AI tutorial out there. We're not just copying code. We're using Claude AI as our coding partner to explain every single step, troubleshoot problems in real time, and customize everything for your specific setup. By the end of this video, you'll have your own trained language model, a desktop application to test it, and most importantly, you'll understand exactly how modern AI actually works under the hood. Let's dive in. Setting up a proper development environment is the first real step towards building your own large language model. This is where everything starts coming together. The tools, the libraries, and the structure that makes it possible for your AI to actually learn and function. Without this setup, nothing else will run smoothly, so it's worth taking the time to get it right. I'm using Visual Studio Code for this build, and my AI coding assistant is Claude Code, which will handle most of the setup work for us. To get started, I'll tell Claude to please set up a Python environment for training a language model from scratch. Install PyTorch with CUDA support, transformers library, datasets, tokenizers, NumPy, Matplotlib, and TQDM. Configure everything to use my NVIDIA GPU and verify CUDA detection. Set up a project structure with folders for data, models, and scripts. Once Claude starts working, you'll see it automatically pulling the libraries one by one. PyTorch is the backbone here, since it's what lets our models run and train efficiently. CUDA support makes sure the GPU is used instead of just the CPU, speeding up processing significantly. The Hugging Face tools, transformers, datasets, and tokenizers give us everything we need for working with large language models, from handling data to defining architectures. Lastly, NumPy, Matplotlib, and TQDM cover the essentials like numerical operations, data visualization, and progress tracking. After this setting up, our project window now has a well-organized structure with all the necessary libraries we need. You'll also see confirmation that CUDA is detected successfully, meaning the GPU is ready to train our model. If you encounter any setup issues, Claude might prompt you about your Python version. In my case, I already have Python installed, but it wasn't the right version, so it's asking me to install Python 3.11 and set up a virtual environment to make sure everything runs properly. If your setup already uses the right version, it'll skip this entirely. Once everything's ready and all the dependencies are in place, you've officially built your foundation for AI development. The environment's ready, the libraries are installed, and the system's configured for training. In the next part, we'll move on to preparing the dataset, the information our model will actually learn from. Before any AI model can learn, it needs something to learn from. And that's why we need to prepare a training dataset. This is like giving your model a large library to study. The more high quality and structured that data is, the better your model's understanding of language will be. In this part, we're gonna set up that learning material and prepare it in a way that our model can actually understand. I'll ask Claude Code to please create a data pre-processing pipeline for training a language model. Download a small text dataset like 500 MB to 1 GB, like Wikipedia subset or public domain books. Implement GPT-style tokenization to convert text into numerical tokens. Create data loaders with batching and split into 80-20 training/validation sets. Show sample tokenized outputs to verify it works. Once everything's done, Claude will print a few sample tokenized outputs on screen. You'll literally see how raw text gets transformed into numerical sequences, which is exactly what your model will use to learn how language works. By the end of this step, you'll have a fully functional data pipeline, which will be your first real step into the world of machine learning. Now, the model can't start learning until it has a brain, so we need to build that brain from scratch. Here's where we assemble the transformer architecture that gives our LLM the power to read text, understand patterns, and predict what comes next. We'll be wiring together layers of memory and attention so the model can focus on the right information while it trains. This is the exact prompt we'll be using. Please build a transformer-based language model from scratch. Create a GPT-style model with 100 to 200 M parameters for my GPU. Include embedding layers, multi-head attention, feed-forward layers, and layer normalization. Use 12 layers, 768 hidden dimensions, 12 attention heads. Set up Atom Optimizer and configure for next token prediction. Use mixed precision and gradient checkpointing. Show model summary and parameter count. Claude then begins constructing a GPT-style model with around 100 to 200 million parameters, 12 layers, and 12 attention heads, all optimized to run smoothly on GPU. The architecture includes embedding layers to translate tokens into vectors, attention layers that allow words to reference each other, feed-forward networks for processing, and normalization layers for stability. It also sets up the Atom Optimizer, enables mixed precision for faster computation, and turns on gradient checkpointing to save memory during training. Once it's ready, Claude prints a model summary showing the structure and total parameter count. Nothing's being trained yet. This step just ensures that the blueprint is solid. Sometimes the build might fail, or Claude will ask to modify files or fix a mismatch. That's totally normal. Let's just approve the changes. And if the model architecture doesn't build successfully in the first try, which can happen sometimes, just ask Claude to rerun or fix it until it completes. Then, once you see the completed model summary and CUDA confirmation, that means you officially have the foundation of your own transformer-based LLM. Training is the part where everything finally comes to life. Up until now, we've built the model structure and prepared its data, but this is where it actually starts learning. The process is simple in concept, but demanding in practice. The model reads through the dataset millions of times, guessing the next word, getting it wrong, adjusting its internal parameters, and slowly improving with every step. To make all of that happen, we'll need to set up the actual training process, the part that teaches our model how to turn patterns into predictions. So let's tell Claude Code to please create a training loop that feeds batches through the model, calculates loss, and updates weights. Add checkpointing every few hundred steps. Include loss curve visualization with matplotlib or TensorBoard in progress bars. Train for 2 to 3 epochs or until loss stabilizes. Add validation loss tracking and optimize for GPU efficiency. Claude builds a full training pipeline using PyTorch, complete with a loop that feeds the data through the model, calculates the loss, which measures how far the predictions are from the correct answers, and updates the model's weights accordingly. It also includes checkpointing, so we can save progress along the way, and integrate matplotlib to visualize how the loss decreases over time. You'll see a progress bar displaying real-time updates as the model trains, showing the loss steadily going down. That's how we know it's learning. Now, here's the important part. Training a model like this properly takes time, a lot of time. For smaller tasks, we can train for a couple of hours and see basic improvements. But to get an actually usable, well-performing LLM, training needs to run continuously for several days. In my case, I extended the training time from just a few hours to an entire week. That's the version we'll be showing in the next video, the one that responds coherently and behaves like a real AI assistant. So for now, once Claude finishes setting up the training loop and you see the loss curve forming, that's your confirmation the process works. The model is officially learning from its data, and after enough time, it's ready to generate its own intelligent text. After all the coding, training, and setup, this is where it finally gets exciting. When you can actually use your own language model. We're not just looking at loss graphs or training logs anymore, because we're about to talk to the model and see what it can do. To make that easier, we'll build a simple desktop interface where you can type the prompt, adjust some settings, and watch your AI generate text in real time. Let's tell Claude Code. Please create a Python desktop GUI where you can test the created model. Create an inference script that loads the trained model and generates text from prompts. Implement temperature control and top K/top P sampling. Include adjustable parameters and real-time token by token generation display. Claude then builds a complete desktop application with all the essentials. A clean interface where you can type in any prompt. Adjust parameters like temperature, which controls creativity. Top K/top P sampling, which affects how random or focused the output is. And see each token appear on screen as the model generates text. Once the setup is complete, we can start testing. Alright, I'll try first a classic line, the quick brown fox. The model responded with a coherent continuation, simple but structured, showing that it understands context. Then let's try to type in a custom sentence and tweak the generation parameters a bit. With a higher token range of 500, the response is now much longer and more detailed, proving that the model could sustain extended thoughts. Lastly, let's keep it short with just a simple hi, and the LLM replied smoothly, just as you'd expect from any conversational AI. Everything runs perfectly. The interface is clean, the text generation is responsive, and it's all happening locally on our own setup. This final test confirms it. We've successfully built our own language model from scratch, trained it, and brought it to life inside a working app. And there you go. You just built your own language model from scratch. Not by reading papers or memorizing theory, but by actually creating one step by step with AI as your coding partner. You have seen how accessible this process becomes when you stop overcomplicating it and just start building. Thanks for watching, and if you want to keep pushing what's possible with AI and Python, stick around, and I'll see you in the next one.